Okay, so um, we've been studying matrices now as these um, mathematical objects of their own. They are, you know, we know that hidden in there is the information about a system of equations, but we don't necessarily need to be thinking of them as systems of equations anymore. We think of them as their own objects that we can add and multiply and things like that, and even find inverses of. And now we're really going to get into functions on matrices. Um, and one of those functions is the determinant. So one question might be, the inverse of a matrix is useful. A thought might be the inverse of a matrix is useful, but it is a pain to find it. And is there an easier way to find it than the way that I showed you last time, where you have to split you have the identity matrix on one side and then your matrix on the other, and then you got to do all this stuff, and it takes a whole page. Is there an easier way? And another question is, given a square matrix, what if the inverse, when I say it, I mean the inverse, doesn't even exist, right? So I'm going to get really, this would make a math undergrad student very, very proud of themselves that they could write like this, but I'm just going to describe a set here, and I'm going to call it m to the power of n by n, and it's just a notation to mean the set of all square matrices. And the determinant is a mapping, I think you could call it a function, from this set n by n to the real numbers. And what it does is it'll take a matrix, and we'll call that matrix A, right? And that's a symbol for elementhood, meaning I'm gonna some square matrix, right? Um, maybe something like 1, 2, 3, 4, right? Um, I'm gonna take that matrix and I'm gonna spit out a number, and we'll call that number little r, okay, like 5. So that would make a math student very proud. What happens when you study math is it can get so confusing that you just want to get a general idea of what's going on to get some sort of grounding, and you start out writing symbols like this, with just big sets, and all right, where am I starting, where am I going, where are my functions mapping to, and this can be helpful. But all that means is I'm putting in a matrix when I plug in the determinant. I put in a matrix, and then I get back out a real number. I go from the set of matrices to set of real numbers, plug in a matrix, get a real number. So I almost feel like doing it on my calculator. That actually, it'll show you on the calculator. You put in a matrix and you put in the determinant function, and you hit enter, and you get back out a real number. So it's kind of a good visual there. So um, I'll start with a simple 2 by 2, and just a general formula. A, B, C, D is my matrix. How would I find the determinant? I think of this. I take this times this, and I subtract this times this. So A times D minus B times C. That's my determinant for a 2 by 2. Very simple to find. And then in a little bit, I'll go into how you find it for a 3 by 3, and then for an n by n. And you realize it can be a long process. What are the applications here? Why are we doing this? Well, some applications in physics. If you have something, I wrote here this symbol. This is really supposed to be something called omega, which is a Greek symbol, and it usually represents angular velocity. And I wrote it because I wanted to talk about angular momentum. If I can imagine I have a spinning object, let's say I have a wheel of some sort, or a cylinder, okay? And this cylinder is spinning about this central axis there. Um, well, let's say it was almost like a flywheel that you would maybe make pottery with. I was spinning and spinning and spinning that cylinder. What, how, what is the tendency for it to want to keep going? Like if I we understand that if I were to oh man um, like when you're riding a bike and you just kind of let go of the pedals, the bike will keep going. That's the concept of momentum, or linear momentum, because you're going in a straight line. Well, the tendency for this flywheel to want to keep spinning is angular momentum. And the way that you would compute that in physics is by taking what's called the position vector and then doing something called the cross product, which is really the determinant. So you understand angular momentum, the tendency for something to want to keep spinning by using the determinant. So that's one example. I won't do one because it's kind of involved in, it'll be more confusing than it's worth. Another example is let's say I have a magnetic field. Okay, so let's say it's going like this. So I have my if I have two plates here, if I have a negative charge. I kind of drew this backwards. Usually they don't draw it like that, but and let's say this is a positively charged plate. So let's say I had two metal plates, and I had positive charges on this one and negative charges on this one. What would happen is you'd have oh wait, no, this would be, sorry. I think I'm mixing concepts here. This is a magnetic field, right? Okay. So not necessarily plates there. That would be an electric field. But if I had like an electron and it was or a proton, I just drew a positive charge, and it was moving very quickly at some speed, v, and it was moving through a magnetic field. Now, magnetic field, we kind of know what a magnetic field is. We've played with magnets as kids. Um, they do, there's experiments done in particle physics where they have these big um, accelerators. I forgot the exact name for them, and they'll send these particles through them, and they'll send them through magnetic fields. What happens is that because this thing is moving, it's a positive charge and it's going through a magnetic field, there's going to be a force on this thing. And I think the force is going to go this way. Actually, I might be messing it up, the direction. It might be going the other way. But the point is, the way you figure out the force on that charge is by taking the determinant of a matrix. And so basically, this thing is not going to move straight. That's the point. Is it's not going to go straight through the magnetic field. It's going to either curve off this way or it's going to curve off this way. That's what will really happen if you were to able to see it happen. But the way you actually work out the arithmetic or the math is by finding the determinant of a matrix. Okay. In calculus, if you go further in math, you will end up studying how to find the area under a curve, which really, the area under a curve represents a whole lot more than just the area under a curve. The integral, which is really what I mean when I say that, is the major thing that you study in calculus, the Riemann integral. So if you want to find, so this is regular xy plane, and I have some function here, and I want to find the area underneath there. So f of x dx. And the way I do that is I do something called the integral. Well, you guys have already, I think you've already seen something called polar coordinates, right? Where instead of doing x and y, I think of, I have a bunch of circles, right? Each of them with some radius r. And then to know where I am, I say, okay, I go out to this radius, let's say this is radius 1, and I rotate over 180 degrees from here, and that's my angle theta. So this is a different coordinate system. To change between this coordinate system to this coordinate system, and if you wanted to compute the integral, you would take the determinant of a matrix. This thing is called the Jacobian, and it would consist of something called partial derivatives. So I I'm sorry if I'm throwing a bunch of terms out there. I'm just trying to make the point that this is a useful thing to do. In probability, this might be a little bit more easy to grasp. If you haven't heard it before, there's something called covariance. So covariance, if I just measure two things, let's say I measured the stock market price of or the price of a stock. Let's say it's Apple, right? And this is the dollars, right? And I wanted to know, I wanted to try to figure out how is that related to the temperature outside or something weird like that. Well, what I would do in statistics is I would gather a bunch of data from the past 20 years or something like that of every day, the temperature, or maybe every hour, and then I would plot that data and I would try to build a model. And one thing I would need to know, maybe in building that model, is there a linear relationship? You know, what we really care about in most of applied math, if you're trying to do research, is finding linear relationships, because those are very predictable things, or easy to deal with. So, okay, so I have my money and I have my temperature. There's something called covariance, which says how strong is the linear relationship between money and temperature. That looks like a matrix, and the determinant of that matrix is what's called generalized variance. Yeah. Okay. Let's just get to an example. So let's find the determinant. It's really not difficult of this matrix: -1, 2, -3, and -4. So if I multiply, I just follow this little formula that I wrote here. This times this minus this times this. So -1 times -4 minus 2 times -3. That's going to be 4, and then plus 6 is 10. Okay? So the determinant of that matrix is 10. This already has some meaning about this matrix. The fact that the determinant, that's another application I could have written, that would have been very clear, is when the determinant of a matrix is not 0, of a square matrix is not 0, that means it has an inverse. So that's actually kind of what I was asking up here. What if the inverse doesn't even exist? And that's what you can figure out with the determinant. If the determinant of a matrix is not equal to 0, it has an inverse. It's called non-singular. That's the mathy word for it. Okay? What about the determinant of a 3 by 3 matrix? Well, that's getting a little bit more tedious. So let me do let me do this problem. 2, -2, 0, -3, 1, 2, 1, -3, -1. Okay, this is really example 4 on page 510. So what you would do is we know how to compute the determinant of a 2 by 2. Very easy. So let's just keep that in mind as we do this. What I would do is I would pick a column to start with, and I want to just look at the top row. There's really a lot of ways to do this, but it's better just to pick the top row to start learning this, and say, okay, these are going to be my I don't think these are called cofactors. My coefficients, I guess. So what I'll do is I'll take the number 2 here, And then I'm going to multiply that by the determinant of a submatrix, which is this one here. So I block out everything else. I say, okay, I'm not using all those other numbers. I'm using 2, and then I'm going to find the determinant of 1, 2, negative 3, negative 1. Then I'm going to subtract the next thing. So I'm going to take negative 2 here, and I'm going to use this column. I'm going to block everything else out, and I'm going to find the determinant of what's left, this column and this column, or this subcolumn, I guess. So negative 3, 1, 2, negative 1. Then I'm going to add, and then I block out this one. So it's going to be 0 times, and what's left is this submatrix here. So it'd be negative 3, 1, 1, negative 3. Okay? I don't expect you to clearly get this on the first try. There's a lot of little steps in here that can throw you off. Alright, so what's the determinant of this? It's going to be 2 times negative 1 plus 6. And then plus 2 times 3 minus 2. And then plus 0 times anything is 0. Alright, this turns out to be 10 plus 2 is 12. Okay? So I'm going to do more examples, but that's kind of the idea is you really use the determinant of a 2 by 2 and you kind of build on that, and you can find the determinant of a 3 by 3 and eventually the determinant of an n by n. Okay, so let's break it down into baby steps. If you've ever seen What About Bob, that's from that. Okay. Example 2 on page 509. So let's start labeling things. The book calls a cofactor, it calls these things the cofactors. I thought it used to be the other way around, but I guess not. Yeah, so the cofactor of this, of 2, is going to be the determinant of this times negative 1 to some power. And there might be a better way to remember. For a 3 by 3, if you just remember the terms are positive, negative, positive, positive, negative, positive, that'll be easy. But really, it's negative 1 to the column I'm in. This is the first column, second column, third column. 1 plus the column. Okay, so since I'm in the first column, negative 1 to the 1 plus 1 is negative 1 squared, which is 1. So this is positive. This one turned out to be negative, see? Because it's negative 1 to the 1 plus 2, which is negative 1 cubed, which is negative. So that's what happened there. So I'll try to go real slow here with this one. Okay, so first thing we do is we pick a column. We pick our first column, and we write negative 2. You write the top thing in that column. And then you use nothing else. I'm not using this number, and I'm not using these numbers, 0 and 3. So I'm just using negative 2. Then I got to figure out my cofactor. So okay, plus, and then it's going to be 0 times the cofactor of 0 plus, and now I know I said that was going to be a negative, but the negative is going to come out of here. All that information is just in the cofactor. 3 times the cofactor of 3. Okay, so in the cofactor of negative 2, I write negative 2 times negative 1 to the 1 plus, what's the column? This is the first column. And then times the determinant of everything that's left over. -6, 5, 2, and 0. Okay? This is actually, the question is just asking for the cofactors, so we will answer that, but I'm actually doing more than what the question's asking for. 0, the cofactor of 0 is going to be -1 to the 1 plus, what column am I in? I'm in the second column, times the determinant of 1, -1, 5, and 0. It's everything not in the second column. That's how you figure out, not in the second column or the top row. Okay? And alright, I ran out of room here, so plus 3 times -1 to the 1 plus third column, and then this is going to be the determinant of everything not in the third column and not in the top row. 1, -6, -1, and 2. Okay? Alright, so let's just start computing stuff. -1 to the 1 plus 1 is 1, so this just turns out to be -2. And then the cofactor of this is going to be -6 times 0 minus 2 times 5. So -6 times 0 minus 2 times 5 is, it's going to be 10, but going baby steps. Really, this is all going to turn out to be 0 because it's 0 times a bunch of stuff, but for the sake of the problem, they're asking for the cofactors, so we just got to figure out what all this stuff is. What is everything next to 0 is the cofactor of 0. What's everything next to -2? What's all this stuff? That's my cofactor of -2. So plus 0 times -1 to the 1 plus second column. So this is -1 cubed is going to be -1. So I can write my minus symbol out here now because I know it's all going to be negative. The determinant of this is 1 times 0 is 0. So 1 times 0 will give me 0 minus -1 times 5. Alright? Then this is going to be -1 to the 1 plus 3. That's -1 to an even power, 4. So that's plus 3 times 1 times 2 is 2 minus -1 times -6. Okay? Continue. -2 times, okay, so we're answering the question now. What is the cofactor of -2? 0 minus 10. So the cofactor is right here. Cofactor of -2. 0 times, this all turns out to be 0 minus -5, so it's positive 5. This is the cofactor of 0. Plus 3 times 2 minus 6, when I'm done there, whoops, I should have worked it out, sorry. 2 minus 6 is -4, so that's the cofactor of 3. Okay, so this is what example 2 was asking for. We've answered the question. If we want to go further and actually find the determinant, we'll do that. So the determinant is just now do the arithmetic. -2 times -10 is 20. This is obviously 0, and then this is going to be -12. So this turns out to be 8. So this is the determinant. Right? You're supposed to end up with a number. Okay, so that I'm sure there's a lot of little steps in there. So you just need to do a lot of examples to find the determinant of a 3x3. All right, let's see. Let me do example 3. This will be page 3 in the notes. So it says evaluate um, so oh, these vertical bars, yeah, I should have said that. Notation can be really subtle sometimes. Um, evaluate, excuse me, um, 2, -2, 0, -3, 1, and 2, 1, -3, and -1. Okay? So these vertical bars, when they're written like that, actually means to find the determinant. So before they were writing matrices as I think they just put little brackets here instead. Now that they're just vertical lines, that actually means that's the notation for finding the determinant. Excuse me. Okay, so again, we do 2 and block everything else out, and then do -1 to the 1 plus 1 power times the determinant of this smaller thing. 1, 2, -3, -1. Excuse me. Okay. I'm sorry. Plus, now -2 times -1 to the 1 plus the column that I'm in, determinant of -3, 1, 2, -1, plus 0 times -1 to the 1 plus column I'm in, determinant of everything else that I'm not using, right? So visually I'm blocking everything else out, and this tells me what sub matrix I write here. Okay. Now once I see, I like zeros, right? We like ones and zeros when we're doing linear algebra and matrices and stuff. So that tells me I don't even have to bother with this anymore. The whole thing's going to be 0 because 0 times anything is 0. So I don't have to worry about two terms. So this one's always going to be positive because it's 1 plus 1 is 2, so -1 to the 2 is positive. The determinant of this is -1 plus 6. Alright, this turns out to be negative, but negative times a negative gives me +2. The determinant of this is 3 minus 2. Alright, and then we'll just write plus 0 just to remember that this guy was here. We don't want to forget him, but it's just 0. So 2 times 5 is 10, plus 2 is 12. Okay, there's my answer. Alright, that is really all there is to it. I'm not sure how much more I can explain that. A lot of the problems are just trying to get you used to figuring out what the cofactor is and everything. So I'll just do some problems from the book. Number 1, page 513. It says evaluate the second order determinant. So these we like. 5 times 3 is, so 5 times 3 minus 2 times 4. Right? You can draw it like this. This times this minus this times this. Turns out to be 15 minus 8, which is 7. Right. I'll do number 3. 3, -5, -7, and 6. 3 times 6 minus -5 times -7. This is 18 minus 35 is 17. Okay. All right, let's do numbers 7 through 14. Those are helpful. Let me try to do number 7. So what it is you're given this matrix 5, -1, -3, 3, 4, and 6, 0, -2, and 8. And they're not actually um, asking you to find the determinant in number 7. They're just giving you this matrix and then ask you things about the determinant. So A11, first of all, write the minor of each element given in problems 7 through 10. So A11, remember how we write a matrix in general? A11, A12, dot 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 dot, A1n, and then so that's A11 is the top left element. So that's 5, right? So what is the minor of 5? Well, the minor is that submatrix. That's what they mean by minor. So, or actually, it's the determinant of that submatrix. So the answer is really the determinant of 4, 6, -2, and 8, which is going to be 4 times 8 minus -2 times 6. So that's 32. Hello. Sorry about that, everybody. Okay. Let's recap, since obviously I wasn't in the screen the whole time. For numbers 7 through 14, you're going to, they just want you to analyze things about the determinant of this matrix: 5, -1, 3, 3, 4, 6, 0, -2, and 8. And they say, write the minor of each element given in these problems, leave the answer in determinant form. So they say, what is the minor of A11? And A11 is the top left element of whatever matrix you're talking about. So what's the minor of this? The minor, first you got to find what's the submatrix that goes with this thing. That's this here, and then find the determinant of it. So that's what I'm doing now. So the minor of 5, I guess, if you wanted to write it out, is going to be the determinant of this, which is 4 times 8 minus this, -2 times 6, which is plus 12. So it's 44. Okay, let me do another one since I messed up with the screen again. Number 9. Actually, let me do number 10. I'll give one to you. A12. So that's the first row. I have to write the matrix again. So 5, -1, -3, 3, 4, 6, 0, -2, 8. So they're asking for the minor of A12, right? Well, that is the determinant. A12 is right here. So that's the determinant of the matrix made from everything not in this column and not in this row. So that's 3, 0, 6, 8. The determinant of this. So that's 3 times 8 minus 0 times 6. 3 times 8, 24. Okay? Alright, now they say, what's the cofactor of these things? Well, number 11. So what's the cofactor of A11? Well, that's just going to be -1 to a certain power, 1 plus the column that I'm in, right? So A11 is up here, so I'm in the first column, so that's the power, times the minor of A11, which we figured out on the last page. So this just turned out, so it's really just the minor of A11 times a negative sign or a positive sign. That's all. So minor of A11, that was 44. So it's going to be 1 times 44. So it just turns out to be 44. So all you're doing is you're taking the cofactor and leaving it positive or making it negative, depending on what column you're in. Good. Okay. Now let me do one more 3 by 3. Let me do number 15. So I don't even, as you can probably tell, I don't even exactly remember the names of all these things. So it's nice to have names for things when you're first learning how to do it, but eventually you just remember the process, and it just becomes this times this, and you move stuff around, and you get your answer. So just remember positive, negative, positive, if you want a quick way, if you're getting used to it. So it's going to be 1 times the determinant of, block everything out, 4, 3, negative 2, 1, plus 0 times the determinant of, I don't even care, because it's 0. So this all turns out to be 0. Plus 0, because now I'm in my third column, times the determinant of, I don't even care, because it's all 0. So we like zeros, you see? And we'll learn in the next section that there's tricks for finding faster ways to compute the determinant. So let's say that this row was actually in the second row. Let's say these two were switched. I can do a row operation and then just multiply by a number, my determinant by a number, and I'll get the same thing. So there's a way of preserving the determinant with row operations and then finding an easier way to compute it. So I could have just switched these two and then I think multiply by -1 and I would have gotten the same answer. You'll see when we get to the next section. But okay, so determinant is going to be 4 times 1 minus -2 times 3 is 4 plus 6 is 10. So that's that. All right. Good luck.